We're going to start with Dr. Ray Bonaqist. Ray is the COO of Advanced Asphalt Technologies.
All right, what I've been asked to talk to you a little bit about is balanced mix design. And so, this is something that's a little bit new in our industry, but I think if you take a look at this and think about it carefully, it's probably a subject that we've been dealing with for quite a while and have just decided now to give it a name, a neat name. The major players, one of the things I want to say about this is my company and I really haven't done a lot of work in the balanced mix design area. The major players in this really have been several state highway agencies. It's really the state highway agencies that have been kind of pushing this with their local research people at their universities. And then within a group that I'm actively involved in, the FHWA Expert Task Group on Mixtures and Construction, we put together a balanced mix design task force. It's quite a large and active task force that is chaired by Shane Buchanan from Oldcastle Materials. There are about 26 members of the task group, and as you can see, it's actually dominated by agency personnel, where there's about 11 agency members, five industry members, 5 research members, a few consultants, and then the FHWA. And really the goal of the Balanced Mix Design Task Force is to try to provide some type of leadership in this area of balanced mix design. And so information that comes out of the task group is available, or information that comes out of the expert task groups is available on NAPPP's website there at that address, at that web address. Okay, one of the major products that has come out of the Balanced Mix Design Task Force is FHWA technical brief on balanced mix design. This brief has been put together and it's currently under review by the FHWA. Hopefully we'll see it published shortly. And this presentation pretty much follows what's in the technical brief. Okay, the major elements of the technical brief is a section on what is balanced mixture design, what are we talking about. There's a balanced mix design example in there. There's some information on states that are currently doing balanced mix design work, and then there's some future work or some ideas of what we're going to do in the future in this area. So the outline that I have for today is pretty much follows that. What is balanced mix design? Then the second thing is, why has it become so popular today? I think that's an important thing to go over. Then what I'll talk about is balanced or performance testing for balanced mix design. What you'll see is that balanced mix design really is based upon principles of running performance tests to check mixtures for rutting and cracking resistance. I'll go over a couple of examples and talk a little bit about what's going on as we move forward. So balanced mix design, from the technical brief, the definition is an asphalt mix design that uses performance tests on appropriately conditioned specimens that address multiple modes of distress, taking into consideration aging, traffic climate, and location in the pavement structure. So really the idea behind balanced mix design is to produce mixtures that are appropriate for the given conditions. Okay, what you may want in a surface course mixture for rutting and cracking resistance may be significantly different than what you would want in a base course mixture on a stiff pavement. Okay, so the idea is to use performance testing and appropriate criteria to address the various modes of distress that you expect to see, where you would expect those criteria to be different depending upon the layer in the pavement that you're working with, surface, intermediate, base, okay? There are 3 approaches that kind of lay out there with respect to producing balanced mix designs. The simplest is to do a volumetric mix design and then run some performance tests at the end. A little bit more complicated would be a performance modified volumetric design where you allow the volumetric criteria to vary based on the performance data. And then finally, there is one that would look at performance design, where you're going to design the mixture based on the results of the performance testing, and the volumetric properties are going to be what they are. And what you can see across the bottom is, as you move from left to right, there's increasing flexibility for the designer to design the mixture. So with a volumetric mix design alone, you're going to meet a series of very specific criteria on the volumetric properties of the mixture. As you begin to add performance testing, there's more flexibility on the materials you can consider and more flexibility on the properties of the mixture that you can produce. Okay, so I'll go into these a little bit more in detail. This is a flow chart that's within the FHWA technical brief. This particular one is for the volumetric design with the performance testing. In this approach, what you're going to do is you would do the current volumetric design as we do it now in AASHTO M323 and AASHTO R35, and you will come up with an optimum binder content. Okay, then you would perform the performance testing for cracking and rutting resistance at that optimum binder content. If it does not pass the criteria that are given, then you redesign the mix and start over. Okay, so you would go through another volumetric design, then followed by running the performance tests again. And in this case, you have to meet the volumetric criteria as well as the criteria for the performance testing. So if you can think about this, this actually puts greater limits on what you can do as a mixture designer. Okay, you meet the volumetric criteria, you also meet a series of performance criteria. With the performance modified volumetric design, what is done here is the volumetric design is done at the beginning and really serves only as a guide. Okay, so what you would get is an optimum binder content. You would then conduct performance testing at multiple binder contents, let's say around that optimum. And then the composition of the mixture that you would finally design is adjusted based on the results of those tests. And in this case, then the volumetric criteria, you don't necessarily have to comply with them. You simply have performance tests that you're going to base your decision for the binder content or the properties or composition of the mixture. Okay, so this provides a little bit more flexibility in actually performing the design. And in the final one, which is a performance design, you're going to perform the suite of volumetric or suite of performance tests at various binder contents or various compositions, or let's say different levels of polymer modification or something along these lines. And then based on the results of those tests, you're going to select an optimum composition that you're going to then use for paving. And in this case, the volumetric properties really are determined as the last step. And again, there's no requirement to really adhere to the AASHTO volumetric properties at that point. Okay, so those are the three approaches that are out there, and various states have attempted each one of these, and I'll go into that in a little more detail later. I think one of the big questions that we have right now with respect to the balanced mix design is the concept is really fairly good for the laboratory design of the mixture. The big question comes about what about the quality control and the acceptance of the mixture. Ideally, what you would want to do is have some type of an acceptance plan that is based on the performance testing that you're going to run. The issue that occurs is that the testing takes time, particularly if you're going to condition samples to represent long-term aging. You're going to be doing this type of work after the fact, and you're going to have to be doing it at a reduced rate compared to what we currently do in acceptance testing now based on volumetrics. So I think this is a big issue that sort of is driving the types of performance tests that I'll talk about now, or I'll talk about in a little bit. The next area that I want to discuss a little bit is why balance mix design now. And I took this slide from Shane Buchanan. This was a survey that Shane sent out to the companies within the Old Castle organization. So there were about 40 companies that responded in 30 states. And I think what we see up here pretty much represents what a lot of agencies are experiencing right now. You know, the issue that seems to have risen to the top at this point in time are issues associated with the cracking resistance of our mixtures. If you look at the responses over there, the rutting and moisture damage are down at the bottom, where 7% of the companies that were responding said this was an issue, a type of distress that they were seeing. But what you see up here at the top is things such as cracking, various forms of cracking, and raveling. Okay, and so I think this is what's driving us in the direction of using the balance mix design, and what has driven agencies toward using balance mix design. Some of the things that we've been seeing over time is, I think, within the SuperPave design system, the AASHTO M323, what we see are mixtures that have lower binder contents, a tendency to have lower binder contents than what we've seen with, let's say, Marshall mix designs in the past. Okay, so this lower binder content, the lower volume of effective binder in a mixture, that tends to produce mixtures that are more susceptible to cracking and durability problems. There's also been an increase in the use of recycled binder. Lots of recycled materials are being used, recycled asphalt pavement, recycled asphalt shingles. These are sometimes used in combination with rejuvenators and softening agents. These types of mixtures, you really cannot assess their performance based on binder properties and volumetric properties alone. So there's been a drive toward having performance testing, again, to mitigate issues associated with cracking. And then there are other types of additives that are being added to mixtures, fibers, ground tire rubber, many different other types of additives that, again, you cannot look at them by looking at binder properties and volumetric properties alone. So this is driving us in the direction of having some types of performance testing within our design system. So what performance tests are out there and what has been used in balance mix design? There's basically two types of performance tests that are used. One set of testing is done for rutting resistance. A second set of testing is done for cracking resistance, and I'll go through sort of what is the state of the performance testing arena at this point in time. I think there's general consensus within our industry that rutting resistance tests work. And it really doesn't matter what rutting resistance test you use. I think that we're convinced that the rutting problems that we see in pavements are fairly easy to take care of. The most common tests that we see out there with the balance mix design concepts are the Hamburg and the APA, the wheel load type testers, then followed by the flow number test. And so I've got photographs of these various tests up there. There are some recommended criteria in an NCHRP report that was done on mix design. This report's 673. These are a collection of criteria that have been developed in various states that are using these rutting performance tests. An interesting thing is that particular research, or that particular report, also includes criteria for a very simple high temperature test, indirect tensile test that was put together by Don Christensen, who works for our company, for PennDOT at one time. And so that criteria is in there, and the reason I bring that up is, as you'll see, I think that we're trying to simplify as much as we can this testing with the idea that potentially something of that nature could be used very simply in quality control and acceptance after you make the specimens that you do for normal volumetric acceptance. And you'll see that sort of concept is coming about in some of the cracking tests now. With respect to the cracking tests, unfortunately, what I can report to you about those is that there really is no consensus on a cracking test. Okay, and I think there's a couple of reasons. One is the cracking mechanisms that occur in pavements are much more complex compared to the rutting problem that we have. You've got different modes of cracking. So you can have bottom-up fatigue cracking, you can have top-down cracking, can have reflective cracking, thermal cracking. What I'll do is try to go through some of these cracking tests based on a couple of categories, and I put them in 3 categories down here. Some of the tests use repeated stresses or strains, some of them are creep or strength tests, and then recently what we've seen a lot of is a lot of fracture tests. And the reason is that the fracture tests are relatively simple to conduct compared to the others. There's a very, very good guide to cracking tests that was put together as part of NCHRP Project 957 that was done at the Texas Transportation Institute. There's a booklet that describes every one of these tests in fairly simple terms. Gives you information on what equipment is needed, the cost, the complexity of the test. There's also a series of videos that were put together by Texas A&M for each of these tests showing the specimen fabrication and then the testing. And there's a link down there at the bottom to that particular project, the results from that project. And the information I have here, some of it comes directly from this guide that was put together. So with respect to the repeated stress and repeated strain tests, the device over on the left, the flexural fatigue test, is the one that has been around for the longest time. This is work that was done by Professor Bonaqist starting back in the 1960s. What you have is a beam specimen that you repeatedly flex, and what you do is count the number of cycles to failure. And from that, you can generate a strain versus number of cycles to failure curve. Very difficult specimen geometry to produce, very time-consuming testing. So it's not run very often. The one in the middle there is the Texas overlay test that a number of agencies have begun to use. You basically glue a specimen between 2 plates with a crack in between them. You move one of the specimens relative to the other, or one of the plates relative to the other end, and you propagate a crack through the specimen as shown there. You can do it in a horizontal mode, or you can do it vertically in some of the servo hydraulic machines. But again, what you're looking at, number of cycles to failure. The issue with this particular test is it does have a high variability. The same thing with the flexural fatigue test. There's quite a bit of variability. More recently, primarily research out of North Carolina State, and a lot of it is being funded by the Federal Highway Administration, is looking at the direct cyclic direct tension fatigue test, AASHTO TP 107. What is done here is you get a characteristic curve. All of the materials or the asphalt mixtures tend to damage in a certain way. You also get a failure criteria from it, and it's another type of repeated loading test. There's a series of creep and strength tests. The low temperature indirect tensile test and the energy ratio test both use the indirect tensile geometry with instrumentation applied to it. What you measure for low temperatures, creep compliance and tensile strength, and you put that data into a thermoviscoelastic analysis, predict cracking. Quite time consuming to do the low temperature indirect tensile test. The energy ratio test is the only one that I know of that is specifically related to top-down cracking. In this case, same geometry. Here you measure modulus, compliance of the material and strength, and calculate an energy ratio, which is basically the resistance of the mixed cracking divided by the potential for the pavement to crack. It's a fairly simple calculation that is done. Then there's the thermal stress restrained specimen test. You put a specimen between a couple of plates, drop the temperature, and wait for it to crack. Since it doesn't move, the thermal contraction is going to build up stresses, and the parameter you get out of it is a fracture temperature. Okay, as you can see, these things all involve a substantial amount of instrumentation, and so do these low temperature disc shape or low temperature fracture tests. There are two low temperature fracture tests that are used: the disc shape compact tension test, which has an ASTM standard for both of these, and then the other one is the semicircular bending test. So you take a specimen, cut it in half, and put a notch. You have a notch in the disc shape compact tension test, and what you're doing is looking at the energy that is required to propagate the crack through the material. Okay, and these are done at relatively slow loading rates, and you have to control the rate that the crack is opening. Finally, there's a series of fracture tests at intermediate temperature where a lot of the instrumentation I've shown you in the previous ones is removed. There is a semicircular bending test developed at Louisiana State or at the Louisiana Transportation Research Institute that uses multiple notches, a slow loading rate, and what you get is a critical strain energy release rate is the parameter that comes out of that analysis. There's also one that was put together at the University of Illinois, the IFIT procedure, which is AASHTO TP 124. It uses one notch depth, fast loading rates, and you calculate it what's called a flexibility index, which is the area under the stress strain curve or the load displacement curve divided by a slope of the post-peak part of it. But the idea behind both of these tests is to have relatively simple fracture tests that you can do at intermediate temperatures to get an idea of the fracture resistance of the mixtures. And just when you thought all of the fracture tests were done, there are a couple more under development. And this was interesting in some recent work that's been done by NCAT and TTI, the Texas Transportation Institute. Independently, they've developed tests using the standard indirect tensile test to look at fracture resistance. And the reason I bring this up is like I said with the Rutting tests, if you can use this IDT geometry, it's a fairly simple thing. We make these specimens every day at the plant, and these things can be used in testing. So the cracking, what I can tell you is that research on cracking, trying to determine what is going to be the best type of cracking test to use in the balanced mix design is continuing. There's a second phase of NCHRP 957 that's been approved, where some of these tests are going to go through ruggedness testing and then correlations to performance. And then NCAT has been doing a number of correlations to performance using materials from their test track and from the Minroad project. Okay, so what I'll do now is quickly go through a couple of examples of the volumetric design or of balanced mix design. The first one that I've got up here is the volumetric design with performance testing. This is the approach being taken in Illinois. So down at the bottom, what you have is the volumetric properties. So you're going to design the mix using current volumetric analysis. Then you're going to run two tests, the indirect or the Illinois, the IFIT, the Illinois semicircular bend test to look at cracking resistance. You're going to run the Hamburg wheel tracking test for running resistance. And Illinois is in the process of putting together criteria for those two tests for their conditions. Okay, and this is work that was done at the University of Illinois by Professor Alcati. Okay, a second one is, this is an example of how you would do the performance modified volumetric design, and this is some information that came from TxDOT. What they use is, again, the Hamburg wheel tracking device for running resistance. For cracking resistance, they're using the overlay tester. So if you look at the green curve over the, and then what they do is do a volumetric design at the optimum asphalt content plus and minus 0.5%. They run the performance tests. And so they have a criteria of 12 millimeters in this case for the rutting resistance, which gives you a asphalt content that you have to be below to meet the rutting resistance. Then with the cracking test with the Texas overlay test, what you see is there's a limit of 300 cycles to failure for acceptable cracking resistance. And this gives you a window in which you can select the final binder content of the mixture. Okay, so this is the concept that's been put together in Texas, and this would be performance modified volumetric design, because the mixture may in the end not meet all of the volumetric requirements within that when it's put in that window. Another very interesting idea that has been put forward by Bill Butler from the University of Missouri is an idea of using performance space diagrams. And in this case, what he is doing is he's creating a diagram where you have rutting resistance on the vertical axis, cracking resistance on the horizontal axis. Increased rutting goes down in this case, but what you can have are zones within there where there are various types of mixtures. So the upper right-hand corner are very rut-resistant, highly flexible, fracture-resistant mixtures, things like SMA, various types of surface course mixtures you may want to use. The one down at the bottom right is going to be a soft mix, not very resistant to rutting, but highly fracture resistant, so maybe use that in a reflective cracking situation. The upper left is going to be stiff mixtures, which you might want to use in base courses or intermediate courses. And then probably the bottom left-hand corner is the area that you want to stay away from, where you have high rutting and high potential for fracture. So I think this is a very interesting concept that Bill's put out there of designers looking at what space do you want to be in based on what mix you're designing, where you're designing it. Okay, so now for the end, future a little bit more. More agencies, I think more and more agencies are getting involved in the balanced mix design area. I would say the ones on the left, California, Texas, New Jersey, Louisiana, and Illinois have been the pioneers that have kind of pushed this effort. And then more recently, the ones on the right, at least within information that I've had or people that I've talked to, have some ongoing work in the area of the balanced mix design process. So I think what we'll see in the future is more and more agencies become interested in this. There is an NCHRP project which has recently been advertised. Proposals have been received, and I think a contractor has been selected, but I'm not sure who that is, on developing a framework for balanced mix design. This was a problem statement put together by the Balanced Mix Design Task Force. And the objective here is to put together a framework that'll help additional states get an idea of how they want to enter into this balanced mix design arena. And then finally, some other activities. The task force is going to continue its leadership role. Shane is quite active with the task force. He has a monthly call to all the members of the task force, and there's quite a bit of work that they're doing. An interesting thing that I just became aware of is that NCAT is now offering balanced mix design training. Okay, there was one course I think in March, and they're continuing to put on courses with respect to balanced mix design. And then the last thing I have is NAPPPP is going to have a conference in Atlanta on paving for performance, design to perform. And there will be several sessions in there dealing with balanced mix design and performance specifications. Okay, and so that's all I have. And if there's time, I'll answer any questions you might have, and if there's time for discussion, we can.
Derek Neer, Plant from Maine DOT. I know it's probably a difficult question to answer, but do you have any advice for states or agencies that are looking to get into, haven't really looked at the cracking so far, and you're looking at 10 plus tests that are options? Do you think it's going to be better No, it's the question that we always ask because
No,
we have 10 different cracking passes.
Yeah, no, I think it's a very good question. You know, I think the first thing that I would probably consider is, you know, what is the mode of cracking that you're seeing? I would certainly look at a different type of test for thermal cracking versus some of the load-associated cracking. If it's a thermal type of cracking, I think you want to head in one direction where you're going to look at the cracking tests at lower temperature. And probably from what I can see, something like the DCT test, and maybe Ben will talk about this more, I think, you know, has a lot of potential in that area. No? No? Okay. That was yesterday? Okay. But you did talk about this? So it does have some potential in that area? Okay. So, you know, that's one thing if you're going to look at low temperature cracking. If it's some type of a load-associated cracking, then I would look at one of the fracture tests at this point. You know, based on the things that I've seen so far, I think that the concept behind the Illinois test, the IFIT procedure is pretty good. I think the issue may be that the loading rate is very, very fast and the temperature is the same. They recommend a 25 degree C test at a very fast loading rate. So I think it's gonna be problematic with many different mixes. I've been seeing information where there are very low flexibility indices. We did some work for Wisconsin where we ran that test at a much slower loading rate, and I thought we got very good data. But I would suggest if you're going to look at that test, to look at different temperatures and loading rates to try to come up with something that seems to fit what you're seeing in the field at this point. Yeah.
I'm just going to make a comment because performance testing seems to be a really big item. And, you know, all the states are talking about what direction we want to go. My only concern is, and I'm seeing a lot of this now, is when you consider a performance test, there's a certain set of priorities that you need to follow. Number one, it's got to be related to performance. Number two, it has to be sensitive to changes in mix properties.
Right.
Number three, it has to be repeatable. Number four, it has to be available. And finally, the least important, it has to be simple and easy to run. Unfortunately, I'm seeing that role being reversed. And I see more and more discussion on how simple and easy tests are and how inexpensive they are. But if we just want feel-good tests, we can come up with a lot of things if it's not related to performance. So I just caution against that. I've said this in more than one meeting before. And as you go down that road, you start to look at performance tests, whatever it may be. And it's, you know, the holy grail is a simple, quick, easy test that's related to performance. I personally haven't seen that yet, and I think we just got to be very cautious as we move forward. That's all.
Yeah. Yeah, I think Greg's right about this, and I think another thing, maybe I didn't bring this out, is a lot of the testing that we're using in the balanced mix design arena, I think really would classify as an index test, okay, where you're trying to get some idea of the performance. You know, a lot of it was developed by people at universities, so there tends to try to be a lot of theoretical considerations behind the test. But I think in the end, really those fall away. And all of the fracture tests right now that I think I put up there really are an index. And so, you know, it's got some engineering units to it. And if you follow the development of them, you're going to see that there's some theoretical considerations, but I don't think that you can necessarily say these tests are better on a theoretical basis or not. So I would rank them like the Hamburg wheel tracking test. It's an index test. It's an index of rutting resistance, an index of cracking resistance. You know, work that the FHWA is doing on performance-related specifications and computer modeling of pavement performance. These are much more theoretical, but again, they're going to take much more time to complete those types of designs. All right, thanks.